Okay, so we have the tropical storm kind of raging outside, and so we're doing this online today, and that's fine. We've moving on to basically chapter what is it, 8, 9, 9 at this point, and chapter 9 is dealing with alkynes. Oops. You see, you think that if I was recording this, I would have prepped this all right, but I just got done recording my Gen Chem lecture, right? So anyway, so here we are with alkynes. Now, here's how this chapter is going to work, right? Alkynes are going to be the same as alkenes, but twice. And that's the general rule of it. Okay, so I just finished the lecture in 30 seconds. I'll see you guys on Wednesday. But that's basically what it is, okay? Now, as you guys have known, you've known me for, this semester longer, then there's a little bit more behind the scenes with this too, but that's the basic idea with this, okay? Because remember, when we were dealing with an alkene, okay, it was the pi bond that was reacting with something, okay? Right, we take our pi bond, the pi bond acts as a nucleophile, or it can act as an electrophile in some cases that we'll learn, right? But the pi bond does a thing, and it's what gets reacted, right? So if we have an alkyne, right, we have two of our pi bonds there, and so we should expect that they're going to react twice to get whatever we need to out of it, whatever those x's may be, okay? And that's going to be mostly true for the things that we're going to be dealing with. Now, remember, one of these things that I'm trying to get you guys to think about is that we've really only learned 3 reactions: addition, substitutions, and eliminations, okay? So if we're dealing with an alkyne, right, if this is an addition, then we should expect that that would be an addition reaction also. And that's exactly what it's going to be, okay? So, but we're going to have to think about how these things add. There are going to be some differences with certain reactions along the way, okay? And that's what we're going to start to introduce here. But at the end of it, right, a couple of things to pay attention to is overall, this is the idea. You're reacting both of the pi bonds. We have to do something special to stop this from reacting after one pi bond reacts. And the book talks about this a little bit, and I'll show you where I disagree with the book about this, but don't worry, we'll get there, okay? But essentially, we're going to be reacting both of those pi bonds is what it comes down to, okay? Now, a little bit of, ideas here or thoughts. When you are dealing with an alkyne, okay, one of the most important things, or one of the things that's forgotten, is just where are the carbons, okay? Remember, carbons exist at the beginning and at the end of every set of lines that connect together, okay? So in this molecule here, right, we have 6 total carbons, right? And our triple bond starts at 3. So we would call this 3-hexyne, right? Or hex 3-yne. Either one of those. But don't forget that we have a carbon at the beginning and the end of that triple bond. That's going to be something important. That's what you guys are going to forget, how many carbons there are, okay? So don't lose your carbons along the way, okay? Now in terms of naming, the Y and E ending is what we see when we're dealing with alkynes. And alkynes, we don't have to worry about E and Z or cis and trans. They're linear, right? They're linear molecules, so we can't have a different spatial arrangement of these things. Okay, we can't have a diastereomer, we can't have a stereoisomer of an alkyne, right? They are linear. What else can you do with them, right? In terms of naming, alkynes get priority over alkenes, okay? So we've been learning this kind of order of importance with naming things. So alkynes are going to be more important than alkenes are. So we would give them the lowest priority number, okay? That's all I really want you guys to know about it. I'm not too interested in you guys spending a lot of time dealing with alkynes, right? In terms of the naming. They are useful, right? They are useful, let's say synthetic functional groups, I guess is kind of I was kind of struggling there with what exactly I wanted to say with this. But they are useful synthetic functional groups. And we'll talk about why that is in just a little bit, but we're going to come back to these a little bit later on also, okay? But for the moment, we're going to basically learn the basics, and then we'll talk about some of these other, how do you want to say, more complex ideas that we want to get with these, okay? All right, so let's get down to it here then, okay? So let's think. So hopefully at this point you guys could fill in the blank there, right? Start off with everyone's mostly favorite reaction there. How do we turn an alkene into an alkane? All right, an alkene into an alkane. This is just a simple hydrogenation, right? So we take our H2 and put some kind of catalyst in here. Nickel, palladium, platinum, ruthenium. There's a million hydrogenation catalysts, right? The most common one is palladium. In fact, we see palladium on carbon is what we use in the lab, right? Palladium's stupid expensive. And so what you do is you basically mix palladium with carbon. Not only does that mean you can add less in the sense of there's not as much palladium there, but it also increases the surface area, and that's what makes this go, right? Palladium on carbon is a heterogeneous catalyst, which means it doesn't dissolve into solution, so you can just filter it out at the end. It makes cleaning up easy, okay? But we have some kind of metal catalyst in there. And you do this reaction, right? We learned things that this is a syn addition, right? And that's important. We add both of those hydrogens to the same side. And that's important. Okay, I think I said that it's important twice in about 30 seconds. I think it's important, okay. So now we're gonna really shake things up, right? And I'm gonna ask you, how do you think we would do this? Well, what we're gonna do is we're gonna add hydrogen, and then we need some kind of catalyst. Now it's 5-ish in the morning, but I still heard you guys, gasp in shock and horror at the revelation here. Right? It's the exact same thing, but how many times do I have to add the hydrogen? Well, let's break this down for just a second, okay? Now, this is a contrivance, but it's mostly true. We're going to have to add the hydrogen once, okay? Sorry, let me back up here. We're going to have to add the hydrogen once, and then we're going to have to add the hydrogen twice, okay? This is kind of the name of the game for alkynes. We do the reaction once, and then we do the reaction again, okay? It's a stepwise addition. Now, notice how I drew this, let's say, intermediate product here. You'll notice that I drew it as a cis isomer. Now, why in the world would that be? It's because this is a syn addition. Those hydrogens have to get added to both sides. We can't do anti-addition, right? We can't have this because that would imply that either the hydrogens are added at opposite times, right? And that this would be an anti-addition. So we can't do that with this setup, okay? Next, we can't stop this here. So let's go back to think about how we would physically set this up in the lab. What you would do is you would grab your alkyne, right? You put it into a container with some kind of solvent, THF, ethanol, any of these kind of solvents that aren't going to react with hydrogen. So you put your alkyne into a container with your solvent, and you put a stir bar in there, you get it mixing, you scoop your catalyst, and then you get a balloon of hydrogen, and you tie it up, and you put the appropriate adapter at the end, and you start to just bubble your hydrogen through your solution while you mix it up, okay? That's the simplest setup. How much hydrogen are you going to control if you've got a balloon of it? Well, Dr. H, you could go back and you could measure exactly how much hydrogen you need, and then you could convert that into the volume and get the right size balloon. And no one's going to do that. No one's going to do that, okay? And even if you could, it's not going to actually stop the reaction halfway, okay? If you only put one equivalent instead of two, you're really not going to stop it at the halfway. In fact, what you're going to get is a giant mess, is really what it comes down to. The point I'm saying is this: whenever you run a reaction like this, it's always assumed to be in an excess of hydrogen, even if it's not really explicitly shown in there, right? We assume we have an excess of hydrogen, we just get a big old balloon and we just bubble it through, and then we come back and we check to see that the reaction did or didn't go to completion, right? That's all it really is. So the point to think about here is assumed in excess, okay? So we can't stop it, right? We can't stop it at this intermediate here unless we do something a little bit different, okay? So what's the different thing we can do? Well, let me draw that a little bit nicer. We'll take some H2 and we're going to put a catalyst in there, but what we're going to do is poison the catalyst. Now, what we mean by that is there's a theory that we don't talk about in this class. I talk about it a bit in my bio inorganic course, but it's called hard-soft acid-base theory, right? And hard-soft acid-base theory just deals with, let's see, how do we want to put this? The preference of metals to bind to certain things, okay? So if we think about this in real life, right? So your car has a catalytic converter on it, right? And that catalytic converter's job is to take any incomplete combustion products, carbon monoxide, and complete the combustion over to carbon dioxide, right? So that's its purpose in life. And the way it does this is it has usually platinum or rhodium or ruthenium, some of these expensive metal catalyst beds in there, okay? And now, it's just hypothetical, right? I'm not a mechanic by any way, but if you put diesel into your car, right? Diesel, the way they make it and the way they isolate it and crack and all these kind of things, right? It usually tends to come with sulfur in there, okay? And so if you combust, if you try to combust diesel with a typical catalytic converter, that sulfur is going to poison your catalytic converter, because platinum, palladium, ruthenium, these things love sulfur. They make these really strong bonds, and as soon as you bond that sulfur to those metals, it passivates the catalyst, and the catalyst doesn't behave in the same way. That's what we mean by poisoning it. We add something to this catalyst to passivate it so that we can control the reactivity a little bit more, okay? And the way we typically do this, there's a couple ways that this is represented. We sometimes see this shown as palladium carbonate, right? Or we just call it Lindlar's catalyst, okay? So when you see this kind of notation, we're just talking about some kind of poisoned catalyst. There's other ways forward. You guys can look it up in the book or look it up online. That's fine, okay? Lindlar's catalyst is typically what I refer to it as, but any of these other ways are A-okay, all right? All right, so what does this do? How does this work? What's the point? What's the purpose? Yada, yada, yada. So here's what happens. Now, if we take this poison catalyst, it's going to behave a little bit differently, okay? Now, even if we have an excess of hydrogen, our product here is going to be that. So this poison catalyst behaves differently. Remember, a catalyst changes the reaction pathway, right? It changes the reaction pathway. So our hills and our valleys are at different energies, right, in our reaction profile diagrams, right? That's kind of what we want to think about there. And so it just so happens that if we go through this catalytic cycle with this catalyst, these cis alkenes are at a fairly low energy that we can isolate, okay? So we can actually make this alkene stop, we can actually make this alkyne stop at the cis alkene. Now we change the catalyst, but we don't change the type of addition. This is still a syn addition, okay? This is still a syn addition. And so those two hydrogens that get added are still to the same side. But the good news is we can stop at that cis alkene, okay? Great. Now I know what you're thinking. You're like, well, I am not happy with a cis alkene. I need a trans alkene. Oops. I need to be able to facilitate this conversion, okay? You can't do this by hydrogenation, okay? You can't do this by hydrogenation for a reason I just talked about, right? These hydrogens get added to opposite sides. So we have to come up with a different way of doing this, okay? And the way that we do this is we take sodium and we dissolve it into liquid ammonia, okay? So typically you'll just see Na over NH3 like this, right? Or Na NH3 like this, okay? So we take chunks of sodium and we dissolve it into liquid ammonia. Now, this is actually a useful setup for a couple different things, right? We see this kind of setup for a couple different reactions, but in all of these cases, these are reducing conditions, okay? Sodium, this is not sodium as an ion, this is sodium in its elemental form. And remember, sodium in its elemental form has that one valence electrons that it wants to get rid of, okay? And it will get rid of it to pretty much anything you kind of put in its path, right? And it'll get rid of that it'll get rid of that lone electron and give it to that triple bond. And it just so happens that ammonia is really good at dissolving these kind of species, okay? So these are highly reducing conditions. All right, so how does this work, or what's the point, or why don't we learn this mechanism? We're gonna learn this mechanism in the next chapter, okay? But this all deals with radicals. Now, what I would recommend is that you guys go through and take a look at what the book is talking about for these things already. Because we will come back and we will learn this mechanism next, okay, in the next chapter. And we'll talk about, then we can come back and assess how this works. But for the moment, I'm just going to tell you guys it works with radicals. And remember, we're dealing with radicals, we're dealing with unpaired electrons, a single electron, okay? And we're going to have to learn some different, let's say, toolkits to deal with those, okay? But anyway, what's the purpose here? How does this work? What's the point, right? Just to clear this up, we can take a we can take an alkyne, and turn it into an alkene in the trans configuration, okay? So to get all these ideas together on one nice summary here, H2, right, Lindlar, right, and then we have the complete conversion, H2, let's just use palladium today, and there it is, okay? Fantastic. Okay, so that's kind of the introductory idea for alkynes. They want to react twice, and we have to do special things for them to react only once. So both of these are going to stop at these alkenes. This one here typically does other things, okay? That sodium in ammonia, we will see that in a different reaction. We just see that it continues to react, although it's good enough that we can stop it at that alkene there, okay? And that's just fine. All right. So, moving on. So, can you guys do that? Can you guys do that mechanism, right? And the answer to both of those better be yes. Okay? So take a quick second, see what you guys can walk through for that one there, right? I'll give you the 3 seconds to pause and then come back. Simple enough, hopefully, right? We just HBr it up. We have a strong acid, cation forms, Markovnikov addition, all that kind of stuff that goes with it. Great. Now let's say we do this with an excess of HBr, okay? What's my product going to be for this? Pause and do it, okay? And remember that when we're reacting alkynes, you do the reaction twice sequentially, okay? So see if you guys can figure out what the product's going to be and draw the mechanism to get there. The mechanism's the same as for the alkene, but twice, and do it sequentially. Don't skip steps, because when you skip steps, you get to the wrong answer. Okay, don't do that, all right? So, let's do this. Pi bond reaches out, okay? We'll add that, we have this, okay? Now, positive charges on an alkene, for this class, in this context, we're not going to have those shift anywhere, okay? That's not really something we've seen before, these vinylic carbocations, okay? These vinylic carbocations. So they're not going to shift for us, so that's some good news, okay? So bromine is just going to see that vinylic cation and come in. And this is what we end up with, okay? Now we've got more HBr around, fantastic. Let me do this. And now we've got a choice. Here's our choices. Or green, here we go, and we add that hydrogen there. Okay, you guys with me on this one? We have two choices. Put the carbocation here, put the carbocation there. Both of those carbons are secondary. Got it? Both of those carbons are secondary. All right, well, what's going to happen? Well, remember, whenever we form a carbocation, we are always going to form the more stable carbocation, okay? Now, how do we stabilize anything? 5 answers, right? We have our hybridization, we have atomic radius, we have inductive effects, we have our resonance structures, we have, I forgot, did I say radius already? I forget which ones I said, but hopefully, right, let's try this one more time. We have our hybridization, we have inductive effects, we have resonance, we have our electronegativity, right? All these things that go together to see which of these positive charges are more or less stabilized, all right? And so that same idea comes into play here, okay? Which of these is more stable, all right? Well, they're both secondary, okay? Atomic radius isn't any different. It's carbon versus carbon. Carbon is as electronegative as carbon, so that's not the difference. Let's see, the hybridization, they're sp2, right? Inductive effects, well, they both kind of stink, right? You know, but actually this one's better by inductive, right? Because it's further away from the electronegative atom. Remember, inductive effect says that we're drawing electron away from negative things, right? From negative things, right? So this is electronegative, it's going to pull electron density away, right? Which makes this carbon positive, so the further that positive is from there, that would be better, right? Do you guys follow along with this, right? This electronegative, so that's positive. Get that positive as far away as possible. So inductive effects would say that this is more stable, right? But this is actually the intermediate that forms. Why? Well, don't forget, just because we don't draw on there, right, doesn't mean that the positive charges, that the lone pairs aren't there. So we can resonance stabilize this positive charge. And in fact, that's exactly what happens. We form this resonance stabilized carbocation. And then the next bromine can come in. Hits that carbon and pops up that bond, okay? And this leads to our product. So let me draw that here. So our product here is where we add bromine to both bromines to the exact same carbon, okay? So we don't follow this pathway down there. Because of a resonance stabilized positive charge, we see the bromine attack the same carbon that the other bromine is bound to. And this is what's known as a geminal dihalide. Okay? Geminal twin, right? And dihalide just means we have two halogens, and the geminal means they come off of the same carbon. So we haven't really seen this functional group before. And here's why. Because it's not too simple to make, right? We have to have an alkyne to begin with, and then we can generate that geminal dihalide. All right? So that's what it comes down to. All right. So let's say we have this geminal dihalide, and we want to go back to our alkyne. Well, our geminal dihalide is going to be one of the functional groups that can lead us back to our alkyne. And to do this, to do the reverse reaction, NaNH2 over NH3, okay? This is what we're going to need to use. Okay. Now, here's one of these common mistakes that happens. Oftentimes, you guys mistake this for Na over NH3. These are not the same things. They don't behave the same way. Na over NH3 is not going to make that product. Okay. This is for reducing things. Okay. Reducing alkenes and alkynes. So NaNH2 in NH3, okay? Now, whenever I give you guys something new, hopefully the first thing you guys do is look at it. So let's break this down. What do we have here with that NaNH2? Well, we've got our buddy sodium, okay? Sodium is just there to balance charges. So on the top, what we have is NH2 with a minus charge, okay? Well, what do we know about NH2 with a minus charge? Well, let's see. So, not sodium. Nitrogen is a fairly small radius. There's no resonance. There's no inductive effects. It's sp3 hybridized, right? So that's a very localized negative charge. So NH2 is a powerful base, okay? Localized small negative charge, powerful base. When NH2 acts like a base, it's going to pick up a hydrogen and turn into, NH3. So what's the relationship between these two here? This is a base and its conjugate acid. Have we ever seen a setup where we have a base over its conjugate acid? And the answer is every day, right? Every day we've seen this, right? A powerful base over its conjugate acid. This is our typical setup for an E2 elimination. So guess what NaNH2 over NH3 is going to do? An E2 elimination, right? It's the exact same setup here. We just use a more powerful base, and I'll show you why in just a second, okay? But that's all it comes down to. So let me give myself some space here to work. Let me erase this just to avoid confusion. Okay, so when we do this setup, we will get that alkyne out of it, okay? All right, let's E2 it up. Look for that hydrogen next door, okay? There's our first elimination. And here's why we need a more powerful base. So this hydrogen here now, okay, this hydrogen here now is not as susceptible to attack as the green hydrogen up there was. That's a vinylic hydrogen, they behave a little bit differently, all these kind of things, right? So we do have to have a powerful base to come in and be able to grab that pink hydrogen there. And that's why we need our sodium amide. I'm just going to move this. I'm going to try to move this, okay, right? And that's why we need that more powerful base, okay? But we're just going to do the exact same thing again. So the NH2, right, the base comes in one more time. And we do that. And this is going to get us to our alkyne, okay? So when we do this reaction, we need that powerful base. And remember, we're dealing with alkynes, so this needs to be there in an excess. Although in reality, it's going to be really hard to stop it, right? It's going to be pretty difficult to kind of stop this reaction here, all right? But so what's the benefit of the, what have we learned, or what's the ideas here? So the idea here is this. Now we can generate alkynes again from our vicinal dihalides, okay? We learned how to make vicinal dihalides from alkynes, so now we can cycle in between alkynes and vicinal halides, okay? We learned how to make alkanes and alkenes, both the cis and the trans version, okay? So that's kind of the main purpose of what I want to introduce in this video here, all right? So go through, take a look at the appropriate sections in the book, start working some of those practice problems, and the next topic that I want to talk with you guys about, I want to do it in person because it's going to be a little bit different, okay? So maybe a little bit of a shorter class is what it is today. We would have been working on a couple examples, a couple of synthesis problems, but we'll see if we can pick this up in class, all right? So stay safe, I'll see you guys on Wednesday.